Hello, I'm Dr. Gorgon, and today we're going to talk about selection sort. The input to our algorithm is a list L. The expected output is that the list L has been sorted. So this should not return. It should sort the list in place. Selection sort continually finds the next smallest or next largest object and puts it into the correct place inside of the list. We are going to do a maximum selection sort. That means that our first job is to write a maximum function. So next we're going to iterate through each index from 0 to the length of the list. We're going to call that maximum function on all objects from that index up to the end of the list. Then we will remove that object from the list and then insert that object at the current index. So first we're going to write that maximum function. By definition, the maximum that we've seen so far has to be the first element. Then we're going to iterate through the rest of the list, and if that object is larger than max so far, we will set max so far to be equal to object. Last, we'll go ahead and return max so far. And of course, anytime we write a function, we should test to make sure that it works correctly. We print out maximum of L, which is correct. So now we're going to iterate through each index from 0 to the length of the list. The default start value for the range function is 0, so we can just use len in order to find the length of the list that we're working with. At each iteration, we're going to find the maximum of the remainder of the list. We remove that object from the list, and we're going to insert that maximum object back into the list at the current index that we're working on. So things to remember: this is a naive implementation. We don't actually expect it to work, and this particular list that's at the top is a good illustration of why it does not work in general terms. So what happened here? At each iteration, the largest object that was left inside of this list was this 6 that's all the way at the end. But there was another 6 that was occurring earlier on in the list. The way that remove function works, it always removes the first object that it finds that matches. So as a result, this first 6 keeps getting found, removed, and inserted at the current index. We print out L at each iteration, we can see this happen. So at each iteration, that 6 keeps moving further and further into the list. We don't want that. There are 3 potential solutions that students came up with. Let's go ahead and talk about them. So first solution was just don't sort it in place. Instead of trying to insert this object into the correct place in the list, we're just gonna append it to a new list, and then we don't have to worry about whether or not we keep finding the same object over and over again. Second, we could remove M from the sliced list. The third solution suggests that instead of using remove, we can use pop. We're going to take a look at all 3 of these solutions. So the first one is the easiest to complete. We create a sorted list, and then we append that object to sorted list. So you'd think that it just involves swapping out the insert for the append and creating a new sorted list, but there are a couple more nuances here. We don't have to slice the list when we put it into the maximum function's argument, and it doesn't have the solution that we expect, which is that the list is sorted in place. Everything ends up in sorted list, and L ends up empty. We could remove M from the sliced list. That doesn't really work. Here's why. So say that we had our original list. We want to create a sliced list, and then we'll make a change to it. We're going to set the first element of sliced list to be elephant. So when we go ahead and print out both the original list and the sliced list, if sliced list did not create a new list object, but instead was still referring to all of the elements that were stored inside of the original list, the list object should have been an elephant, but it's not. So we end up with a new object every time we slice. That means that when we specifically remove that list object from the sliced list, it doesn't do anything at all to change our original list. And therein lies the problem. In the last solution, instead of utilizing the remove function, we say, well, maybe we should use the pop instead. But as it turns out, you can't pop the object, you have to pop the index of the object. So let's experiment for a minute with the index function. If we find the index of M So the important part about the index function is that it still doesn't really help us because it only shows us the first occurrence, but we can use that. So if we are getting the maximum from I through the end of the list, maybe we can get the index starting from that same slice. It is 2 at the first index, and then the 3 in this last one is referring specifically to that maximum that is all the way at the end of the list, but we need to add I back to it. So if we do that, that last 6 is continuously the maximum because we haven't moved anything about it. So let's try using pop. In this case, we want to make sure that the index that we are dealing with is the index from the slice that we are currently working with, plus I, and we are going to pop the object at that index and insert it back at I. So this last solution works for the algorithm that we set out to make it so this selection sort does not have to return anything, and that means that we can actually put this into a function that does not return at this point. We don't need a new list in order to make this work for solution 3. So we get rid of all of the pieces that we no longer need. It sorts the list in place and does not return a value. So if we want to finish our selection sort, we want to add in a docstring for this. Our purpose is to sort list L in place using selection sort. Our input is our list L. As an output, we have no return value, but L is now sorted.